So first of all, thank you for inviting me to talk to you. And also, I imagine this talk to be uh, somewhat informal. It's not a huge meeting, so please feel free to interrupt any time, and I do my best to answer. So here at University of Colorado, there are two aspects of lunar dust that we are working on. One is the lunar dust exosphere, and the other is the surface dust, uh, surface charging, dust mobilization due to electrostatic effects. But I will leave that for another time or for another speaker. So I will only talk about the lunar dust environment which is above the surface. So I am sure you are all familiar with, the Earth is receiving on the order of 100 ton of cosmic dust every day. We typically sort the incoming dust particles into two types. The meteor showers, specific times you go out and you see shooting stars and so forth. These are the little particles that they remember the orbits of their parents or the source. So they come in well-focused, well-collimated beams in certain periods of the year when the Earth's orbit intersects this torus that the source body would leave behind. And at some point, after a while, due to perturbations like radiation pressure and gravity from the planets and so forth, the small particles decouple from their sources, and we just simply lump them into what's called sporadic background or the sporadic meteoroids. There is still a bit of ordering by arrival direction, apex and anti-apex, helion and anti-helion, whether the particle comes apparently from the direction of the sun or it's rushing towards the sun and so forth. But of course, I mean, this is just a nice picture of shooting stars with a long exposure. If you go to an LS body like the moon and just scale the 100 ton a day, what we are receiving just by the surface area ratio would tell you that maybe on the order of 15, 20 tons would also hit the moon. The moon does not have an atmosphere. So the incoming high speed, these are typically 15, 16, 17 kilometer per sec incoming particles, micron, 10 micron, 100 micron, small dust pieces. They directly hit the surface. And when they directly hit the surface, they generate a plume. A whole bunch of small particles are streaming away from the surface. The typical speeds of the outgoing particles are maybe 100, 150 meter per sec. So most of them will not escape. The vast majority is not escaping, but goes high up and falls back down to the surface. So there was the rest or most of the talk is about this mission that was a couple of years ago by now, the Lunar Atmosphere and Dust Environment Explorer, which carried a dust instrument to kind of map this cloud of dust that is continually raised by the incoming micrometeorites. On the top right is the trajectory of the spacecraft. It started out around 250 kilometer as it went in an elliptical orbit around the sun with the closest and furthest away distance of maybe 220 to 60, and then dropped to a closer orbit, typically 100 kilometer down to 50. And it only lasted 100 days or so, 120 days. So imagine this dotted line would be, for example, an incoming meteorite would generate a puff of outgoing dust. And as the spacecraft goes around the moon, this instrument is pointing in the RAM direction and intercepts the particles as they rise and fall back to the surface. An incoming particle, based on the orbital speeds and the trajectory, would hit this target, hemispherical target, which is about 6 centimeter in radius, so a total surface area of about 100 square centimeter. This is kind of a modest little box. The particle at 1.6 kilometer per sec can generate a small puff of plasma, electrons, and ions. And then the electric field that we set up in this instrument would focus the ions into an ion detector, and the electrons can be recollected on the target. That's how it works. And then these are how the signals look. On the top two trace is the multi-channel plate. That's the ion target and the ion detector. And the target is the electron signal. And these two plots, I hope you could see the mouse. These two plots were, the date is 2012. Gosh, more than 8 years ago. And we were recorded at the Dust Accelerator facility here at the University of Colorado, where we can shoot single particles, and every little particle, the mass, the charge, and the speed is recorded. So we know exactly what hits the instrument during what we call test and calibration. And then the same two signals are at the bottom from space. These were now early 2014. And then, the amplitude and the timing and the shape of these signals would tell us how big of a particle hit the instrument. And this is all the data we collected. Time is running on the x-axis, and the y-axis is impact rate. The top wiggly line is particles that are just above the threshold that we can detect, about 1/3 of a micron in radius. And those particles hit the small instrument at a rate of once per minute. And then if you go towards bigger particles like 0.7 micron in radius, you have to wait about 10 minutes for an impact. But we are continuously recording dust impacts. These blue lines are special periods. For example, the Geminids or the Northern Taurids. We know about that these are meteorite streams that hit the Earth. They should also hit the moon because the scale of these streams is certainly much bigger than the Earth-Moon system. And when the meteorite streams are coming, the amount of dust that we are recording is enhanced. And I will come back to that in a second. So based on the measurements that we have, on the left is all the data that we collected. The color chart is dust density of particles that are at least 0.3 micron in radius or bigger, in units of 10⁻³ per cubic meter. And then there are these black regions where actually we never made measurements. Either the spacecraft never visited, or we shared the trajectory and like a UV spectrometer, either they were taking observations or we were, so we had to share the time available. Also, this part of the orbit from, when you are turning towards the sun, as we went around and around in a retrograde orbit, when the sun is in the field of view, we could not make measurements. So this is all the data that we collected. And then you could use a little bit of math and analytical approximations that this is the average dust cloud density that lives around the moon at all times. It is variable in space, variable in time, as I will show that to you in a second. But on average, this is it. There is a curious variation with as the moon goes around the Earth. These arrows, like the blue one, are the helium source that are appearing, coming, the sporadic background as we discussed, particles that are primarily coming from the sun, and the red ones, the anti-helium coming towards the sun, arriving at the moon, and then the aphelion, the forward and backward directions. Oops. If you put them all together, there is a general stream of incoming particles to the surface. And as the moon goes around the Earth, of course, the Earth goes around the sun 30 kilometers per sec. The moon goes around 1 kilometer per sec. So there is a modulation in speed, 29, 31, 29, 31. And the amount of impact ejecta that we generate is a high part of the incoming speed. So when the moon is rushing towards the incoming stream, the dust density is enhanced. When it's running away on the left side, the dust density is going away. So it's kind of a beautiful piece of physics that we see in the dust cloud density. We record also the orbital motion of the moon around the Earth as the Earth-Moon system goes together around the sun. So let's go back to this impact rate plot and look at these special periods. These were the meteor showers that we recorded. There were many more, but the range of particles these ejecta particles can reach is not very large. So the spacecraft was confined to the equatorial region, plus minus 20 degrees or so. So impacts that appeared way up north or way south, we could not see. December 2013, Chien-Shiung landed, and I'm sure it generated a huge plume of dust way up north, and we could not see the effect of that. But we certainly see the northern Taurids, the Geminids, the Quadrantids, and so forth. For a couple of days, the impact rate is clearly enhanced. There's a nice comparison between the Geminids and then these white dashed line and the white dots are what's called the green lights and the white dash bar are the zenith hourly rates. People on the ground go outside at night and report back how many shooting stars they recorded in an hour. Zenith hourly rates. And then we can lay on top of that the impact rate that LDEX recorded. Those are the white dots. And of course, even this small structure, which is probably due to the segregation by size of a trail or the incoming dust particles from this particular comet that generates the Gemini shower, even that is recovered, and it goes hand in hand what's seen on the ground as a shooting star and what's seen as dust density enhancement in orbit around the moon. There is another interesting comparison. For example, the rates that we are observing as a function of time, and then the density of sodium and potassium that the ultraviolet spectrograph was noticing. Then you could do a little bit of what we call a correlation study. And it turns out that for whatever reason, sodium is not necessarily driven by the sodium density. The impacts are not necessarily a major contributors, but they certainly seems to be the case for potassium. And this is just a very simple-minded cross-correlation study when we argue that the potassium density and dot will change in time proportional to the meteorite impact that is coming in, and it has a characteristic lifetime that it will settle back to the surface after several bounces. And it turns out that it's about 5 days or so, the correlation between the impact rate seen by LDEX and the potassium density recorded by UVS shake hands. So for potassium production, dust impacts to the surface must be more important than for sodium. It could be that sodium has a much longer lifetime, or sodium is doing something different as it bounces on the surface than potassium does. So this is a little computer simulation of how an impact ejecta cloud looks like. These are dust particles at the dust density as it is rising above the surface and eventually would fall back down. And on the top is the impact rate that you will record if you fly through over one of these plumes. That happens several times that we recognize this kind of a shape. It's asymmetric because it takes a couple minutes to go across the plume. So the density is changing in time. So early on, you will see more dust particles than later. Also, these particles are flying into the detector. So our threshold is somewhat lower. We are recording smaller particles as opposed to on the exit side, those particles are running or moving away in the same direction as the spacecraft. So the impact speeds are somewhat lower. So here is a dozen or so of these plumes that we detected. They are all different plumes, but they were recorded at different heights. But notice this picture seems to hold together because the impact, the plume angle, the opening angle, makes these plumes wider and wider if you record them at higher altitude. So that's kind of nicely hangs together. But there is something really important about this, because if you detect a plume, you could certainly figure out where it came from the surface. Typically, the height of the spacecraft is the spatial resolution that we can detect the footprints where we can detect particles from. So imagine that this is, for example, the North Pole and the South Pole of the Moon. And these dark regions are regions where sunlight never enters. This we call the permanently shadowed regions. But as far as interplanetary dust impacts go, there is no permanently shadowed anything. They hit at all times, at all places. So if you were to have a dust instrument that would measure, in addition to mass, the composition, you would have no problem looking into a permanently shadowed region as you fly over this, and then could detect particles that were elevated from regions where the sun doesn't shine. And these permanently shadowed regions are of great interest because people argued for a long time that these are places where volatiles, including water and CO, can collect. It's like a sand trap. If you hop on it, various bounces, like a water molecule, as it hops, if it lands in a permanently shadowed region, then it can probably stay there. However, of course, there is a curious balance of collecting volatiles and removing volatiles due to meteorite impacts. And that balance have yet to be figured out because we don't really have a good understanding what hits the moon way up north and way down south. Even on Earth, that data set is much more sparse than at lower latitudes. This idea that you could make a surface map from dust particle impact. Oh, I'm sorry, we cut out. Let's see if I can quickly fix this. Oops, not quite. Let's try a little further. There is a NASA flagship mission searching for habitability of, signs of life or so at the moon, at the Jovian moon Europa. It's one of the Galilean icy moons of Jupiter. We know it has an undersurface ocean, and we know that there is an ejecta cloud engulfing it because that measurement was done by the Galileo mission like 2 decades ago. And as an instrument, as the spacecraft would have close encounters, depending on the track it follows, it can identify regions of interest like a plume or freshly resurfaced patches, and then it can tell you the composition, make a surface composition map based on detecting dust particles. So how do you do that? How would you tell me the composition And the last couple of minutes, I would like to tell you about instruments that we work with. The first one is the Cassini Cosmic Dust Analyzer. Here it is. A dust particle comes in, and there is a little target at the very bottom. If you hit there, there is a grid above it that would accelerate the ions towards a multi-channel plate and collect the electrons, just like LDEX did. And it's called a linear time of flight, because this acceleration, the energy gain of an ion is much more than its thermal spread or the initial velocity distribution it gains from the impact plasma. So roughly everybody is singly charged. Everybody gets the same charge times the electric field. So all has the same energy. But then if you have half mv squared, the same for everyone, if m is big, v have to be small. So big fat ions will run slow, and light ions like hydrogen and helium will make this trip much faster. And that can be organized as a time of flight mass spectrum. On the bottom axis here is microseconds in the time it took from the impact to get into the ion detector. And that is kind of an arbitrary unit, the currents that you are collecting as a function of time. And then you could identify this as carbon and oxygen. And this is a region where sodium, magnesium, and silica lives, and so forth. We cannot quite resolve it. And rhodium is an ion generated from the material of the target itself. The Cassini chemical analyzer had a rhodium target. So of course, this is the technology of the late 70s. And that instrument was remarkably successful, had tremendous discoveries like the undersurface ocean at Enceladus, and the makeup of complicated, complex molecules coming out from the plumes at Enceladus. So even with a modest mass resolution of m over delta m of 30, which is, you know, how close an ion mass line has to be that you could resolve it, it worked remarkably well. There are newer versions of this instrument which would increase the mass resolution from 30 to above 200. And that is by extending the flight path an ion can follow. Here is a dust impact. And then the plasma that you are generate is the ions are accelerated the same way. There is a grid above the target. But then they enter an electrically designed ion optics region where the ions are all focused and turned back towards the collector, the detector in the middle. The very fact that the flight path is longer, and the very interesting physics of ion optics, that if you are faster for some reason, then you penetrate in this electric field a little longer. So you are actually focusing not only space, but also in initial velocity or initial energy. So that device, I'm showing you a lab spectra of platinum-coated pyroxene at the dust accelerator. And just for comparison, for example, you would notice that this device had a silver target. You notice even the isotopes of 107, 109 of silver. So it has a mass resolution that is way superior compared to a linear time of flight. And you can then ask questions about isotopic composition. And for example, here it is magnesium. You see this, the triplet isotopes of magnesium and so forth. So here is another comparison of an interstellar dust candidate from Cassini. And then, of course, we have problems of resolving this big white peak from sodium and magnesium and silica and the various isotopes of magnesium. But in a device like a modern version of Cassini would provide this incredibly well-resolved mass spectrum And then you could identify the makeup and the chemical makeup and even the isotopic makeup, what comes off the surface. So a newer version of LDEX, like LDEX Plus, could fly around the moon and make a chemical map. And of course, we are all very excited. I'm sure you have seen the news release that NASA again discovered water on the moon. Imagine that it's in the form of ice particles, water ice by any chance. And I show you a water ice spectra from Cassini in the earring of Saturn. We know it's water ice, and you cannot mistake chunks of water ice for anything else because it generates this incredibly well-organized series of lines, which is a protohydrate, and then 2 waters, and then 3 waters, and 4, 5, and so forth. It's very well organized as you break up into smithereens into ions of water clusters of various sizes. So I think this is my last slide. Maybe just as a summary, you know, the moon as any other airless planetary body, an asteroid or near-Earth object or Mercury to a large extent, is continually bombarded by interplanetary micrometeorites. And in response, if the body is big enough, like the moon, it can retain these particles because the typical ejector speeds are certainly less than the 2.4 kilometer per second escape speed from the moon. But if you were to go to a much smaller object, like Phaeton, which is a target of an ESA mission, then the ejector particles will simply leave because gravity is so much smaller on a tiny body. So at least the moon is engulfed in a permanently present dust exosphere. It is certainly changing over time and location. And every single little particle from the surface is a sample from the surface and provide an opportunity to map the surface composition and identify available resources from orbit. And my pitch, perhaps the last little statement, imagine that you would carry an instrument like this on a polar orbiting spacecraft, that you could measure the dust composition analyzer, and that could really make a big dent in our understanding what exactly is in permanently shadowed regions for what's called in situ resource utilization, but also maybe there is a record of the early evolution and history of the solar system that we could kind of dig into by measuring the composition of tiny ejecta particles. And that was my last slide. I am open to answer questions if I can.
Was a girl from NCU. He has a question.
I have a question about for the instrument developer, the typical size over the lunar surface is how many micrometer? Typical size of dust.
Oh, the size distribution. I see. The size distribution. First of all, we can detect individual particles at 1.6 kilometer typical speed that have a radius of at least 0.3 micron. The largest particle that we detected in 10 years, I'm sorry, in 6-7 months is about 10 micron.
10 micron.
But I mean, you know, we can work out the statistics. If there are bigger particles, then what are the chances that we will see them? The size distribution seems to be independent of height, and it goes 1 over the density is n of m. I'm sorry?
Density? You need a distribution function or something?
The size distribution is what we detected was independent of height, and the density of a certain mass is inversely proportional with the mass itself. So there were, you know, if you take an r cube from 0.3 micron to 1 micron, if you take the cube of the radius, that would tell you the density ratio of 0.3 micron and 1 micron, for example. Now the instrument, there was a lot of interest in high altitude levitated dust particles. Those would be like tenths of a micron. We could not possibly detect them as a single impact. But the ion detector was actually we were continuously recording the ion signal. So if you had a lot of small particles coming in, we could have detected their collective signal. Every one of them generates some amount of ions. That's not enough to trigger, but it's enough to record. And we could then, if people argued that over the morning or the evening terminator, there's a whole lot of small dust particles, as some statements from astronauts and sketches of astronauts indicated, we would have seen it, and we did not. So that would be down to 0.1 micron in radius. We could not see them around the moon.
Any other questions?
I have a question.
Yeah, please.
Okay, so you mentioned the composition from the ejecta particles. So can we say this these ejecta particles, the composition or the material is not only coming from the surface, but also from the impact like a meteor shower. So and how do we divide or distinguish this environment or composition from those?
So that's a very good question. At Europa, which is an icy moon, from Galileo, we know that the typical zodiacal type dust particle is 100 micron, generating an ejecta cloud that it had a total mass of about 1,000 times more than the incoming particle. And it's distributed into much smaller particles. So the yield from the surface is enormous. Now the moon is somewhat less generous, and we didn't know that ahead of time. So all the calculations were made for yield of 1,000. Around the moon, the yield seems to be on the order of a few tenths, maybe 30. So you're absolutely right. We think that the incoming particle will actually pulverize or break up and perhaps contribute a tiny fraction of the ejecta cloud, but at least 30 times more the material is from the lunar surface.
Mihály, I have a couple of questions. The one thing is that I'm always curious, why LADI's mission lifetime's only 8 months, it's so short? Is there any mission constraint to that?
That's a very good question. It was a cheap directed mission. Every instrument was from a NASA center, but NASA didn't have a dust instrument, so that was competed. But for some reason, the amount of fuel for station keeping and maintaining the orbit was very limited. So this was a mission, I think, by the time it's all said and done, maybe $200 million, which is in the books of missions, it's on the inexpensive side, including the launch and the spacecraft and the instruments and so forth. The instruments, typically represent a tiny fraction of the cost. We had if I go back and show you this plot right here. You notice that there is this blue-green extension, which is, we argued for an additional couple months, and that's all we could get in orbit around the moon. So it was limited in resources, limited in financially. So it was a very short mission. I wish we had a chance to finish at least 1 year. That would have made, to at least go around the sun once and see if you notice asymmetries. But to do these measurements really well, I imagine if you were to be on a polar orbit, you would do much better, because then you could explore the entire surface as the moon, rotates below you as we go around the sun.
So what would be the optimum altitude of the spacecraft?
Well, so, the impact rate of was sufficient for 100-kilometer height. The footprint on the surface is about 100 square kilometer. So if you go down to 50, your spatial resolution will be 50, but the orbit keeping is getting harder and harder. That's my understanding. So it's a compromise of duration, how long you could be in orbit, and what is the spatial resolution that your science would require. Now, typically these permanently shadowed regions are, quite big. So you could look into them, and depends how big of a crater you want to resolve, that would more or less decide the height of the orbit. If I were to think about or proposing or arguing, I would start, 100-kilometer and hopefully a full year in orbit, and then lower the orbit if we can, and have a higher resolution, higher chemical map of the lunar surface that way.
Okay, final question I have is that you mentioned at the end your new design LDEX Plus, and how heavy was the mass of the instrument, and can you tell us?
So I don't have an instrument at the ready, but we could certainly, I think we could keep it under 10 kilograms, maybe lighter. LDEX, this little instrument, was 3.6 kilogram. For IMAP, we are building an instrument like I showed you, and also for the Europa Clipper mission. The Europa Clipper mission version is very heavy, because of the radiation shielding. So that's not a good example. And then the one that we are building for an L1 mission, that's very large. But I think it could be an instrument of 7-8 kilograms. And if we negotiate the mass resolution and so forth, maybe 200 is overdoing it, and maybe 100 would be satisfactory, then we could make it somewhat lighter. They are reasonably inexpensive. There are a couple high voltages, but this is not a complicated device. And the amount of data that we are producing is very modest. It's not like imaging or a spectral instrument. So the data rate coming out of this would be very modest.
Very good. Mihály, you're always a good teacher. So I hope that you will convince NASA to put up this experiment on the lunar mission, in near future.
Even if we could just leaf fly LDEX in a polar orbit, that would be already a tremendous step forward. But it's not in the cards at the moment. So I am not. One day.
And how soon you could build such an instrument? I think you have everything in the lab, right?
Yes.
Okay. I think that it's a very good information, and then and if there's no more questions at this moment, we would close the session. And Mihály, thank you so much. I have some other questions that I could write to you. And don't remember to get me in touch with the survey.
Yes. Yeah. I have two things I written down. One is the survey, and the other is the book proposal. So I will follow.
Right.
Okay.
Yeah. Thank you so much, and have a good evening too. Yeah.
Thank you all. Bye-bye.